welcome on in to video 2. So, as a recap, last video we talked about first derivatives, right, and getting used to parametric equations. And now we're going to just add an easy concept of second derivatives. Ooh, let's see if we can get that to work. There we go. Second, let's see if, there we go, second derivatives. Hopefully that starts to show up better as we continue here. So second derivatives. Now we're just going to add one piece to this, and that is if we're trying to find the second derivative, right? This is the Leibniz notation here, and again we're using parametric equations. Well, this is going to be equal to the derivative with respect to t, right? So this is the derivative operating, say we're going to take the derivative with respect to t of our first derivative divided by dx dt. Right, so not a whole lot to add here. We worked on finding our first derivative in the last video, right? So all we're doing is one more derivative, essentially, right here. We'll have to divide it by something extra, but let's go ahead, we'll jump into an example. So example 1, we'll say x is equal to t cubed plus 1, where y is equal to t squared minus 1. Okay, so first step, again, we're just going to repeat the same process we did last time. Let's go ahead and find dy dx. So as a reminder, right, dy dx is equal to dy dt, and we'll just do this as we go here. So dy dt, 2t over dx dt, which is 3t squared. And I'm going to circle this, right, because we're going to need this later on, right, over here. We'll need this dx dt one more time, but we can also simplify. I'm going to write this as 2/3 1 over t. Good. Okay, so we have our numerator. No, we have dy dx. We still need our numerator. So we need to take the derivative of this piece here with respect to t. I'm going to write this down here. So we need the derivative with respect to t. I think I just wiped this off, so hopefully it still shows up, of 2/3 1 over t. Let's see if we can get this to work a little bit more. Maybe I've used it too much already. Okay, now the nice thing when we're taking the derivative, this 2/3 can go out, so we'll just, and I'll use this one from now on. The 2/3 can jump on out, and so now I'm just taking the derivative with respect to t of 1 over t, or t to the negative 1. So we end up getting 2/3. If this is a t to the negative 1, the negative 1 comes down, and we subtract, so t to the negative 2. So essentially we end up with negative 2 over 3t squared, right? So this is our numerator, right? So again, just to so I make sure I didn't lose anybody, we took our first derivative. This is 2 over 3t. We can also write this as 2/3 t to the negative 1, in case I lost anybody on this point, right? Now I want to take the derivative of this with respect to t. And so what happens is the 2/3 just stays in place. The negative 1 comes down, which is right here, and we subtract from negative 1. So that's how we get that negative 2. Let's see, we'll go back to this one more time. Okay, so we have our numerator. We also have our denominator. There we go, right? And this is going to be, where is it? 3t squared. And so if we simplify this, so we don't have this ugly 3-layered fraction, we have negative 2 over 9t to the 4th. Awesome. Yeah, that looks way better. In case anybody couldn't see this stuff. I think it should be fine now. Okay. All right, so let's go ahead and write this on the side here. dx squared. This is negative 2 over 9 t to the 4th, and I'll kind of box it in so as it doesn't get stuck with everything else. Right, so we have our second derivative. Right, now we're going to answer one more question here. Anybody remember what goes along with second derivatives? Correct, concavity, right? I want to know if this is concave, where this is concave up, where this is concave down. Now, in order to do that, I have to know what? Inflection points. Right, so this is all coming back from Calc 1. In order to find inflection points, I need to set this equal to 0. However, right, this is not going to equal 0. So our other option is either we set it equal to 0 and we find an inflection point, or if we have an asymptote, which we do here at t is equal to 0. Right, I can't plug in 0. This is an asymptote. I want to know what's happening on both sides of this asymptote. So let's say over here, we'll use t is equal to -1. We plug this in, we get -2 over, well, -1 to the 4th power is going to be positive. So we have a negative value here. And we'll use t is equal to 1. Maybe you see where this is going. We're still going to end up with another negative value. So if we have negative values, our interpretation is that this is concave down. Now, some of us might immediately go, well, the whole thing's concave down. Not quite, right? Because that's 0. So when we're writing this, we can say concave down. I'll abbreviate. We have -infinity to 0, and because I ran out of space here, union 0 to infinity. So we're not concave down at 0, right? We don't want to write 0 in our interval. All the way up to 0 on both sides. All right, so again, this is our rule that we've added. All we're doing is we're taking the derivative with respect to t of our first derivative, dividing by dx dt. We already have this information, this information. We just need to take the derivative, right? Once we do that, we found our first derivative. We take it with respect to t one more time. This is how we got our -2 over 3 t to the -1 down here, right? When we do power rule one more time, the -1 comes down. We have t to the -2. This is our numerator piece, right? Which is this. We divide by 3t squared, which is coming from dx dt. We simplified it to get rid of the 3-layered fraction. After that, we wanted to know, where is this concave up? Where is this concave down? Right? We're either looking for when we can set this equal to 0, or we have an asymptote. In this case, we had an asymptote at 0. We test both sides. T is equal to -1, t is equal to 1. We have negative sides on both sides. And so the entire thing, right, -infinity to 0, 0 to infinity is concave down. Okay, so that is example 1. We'll come back. We're going to do another one. Again, the tough part here are the derivatives, right? This case was just a power rule, but we're going to end up doing one that's a slightly more complicated. So I will see you in the next example. Welcome back for our second example. So same idea. We're going to do the same thing one more time. We're going to try to throw in some trickier derivatives just as a refresher. So again, we'll write down this one more time so we get used to it. Second derivative, right? And this is going to be equal to the derivative operator, right? This is saying take the derivative with respect to t of our first derivative that we already found, and we want to divide this by dx dt. Okay. So let's give you some parametric equations to work with, right? Let's say x is equal to e to the t. Nice easy derivative. So let's give you one difficult one. Y is equal to t, e to the -t. Okay. So first derivative, right, dy dx. We know this, so let's get better. We won't write it this time. We know this is going to be equal to dy dt. So what do we have here? Right, we have this product rule. So derivative of the first is going to be 1 times the second one stays the same. So we have e to the -t plus, now t stays the same. We have e to the -t stays the same, but remember the chain rule part here. So times -1. And we're going to divide that by e to the t. Okay, so we're going to end up simplifying this. Maybe we notice that these each have an e to the negative t in common, right? So I'm going to pull this out. So let's see what we end up with here. Now we have, if we pull out an e to the negative t, we end up with just one here. Now we have a t left, and we have a minus sign. So minus t all over e to the t. And if it's unhappy up here being negative, we can move it down to the denominator, and we find that 1 minus t over e to the 2t. This is our first derivative, right? So this is this portion here. Okay, and now the next thing we want to do is take the derivative with respect to t of this. Well, what do we have here is a quotient, right? So we're going to need to do a quotient rule. Let's write out everything here full. We have 1 minus t, numerator, e to the 2t, denominator. So maybe we remember our rhyme, low derivative of high, which is negative 1, minus high derivative of low, which is a chain rule, 2e to the 2t, all over a low squared, which is just going to be e to the 4t. Okay. So far, so good, right? So this is almost our numerator, right? Let's go ahead and see if we can simplify this. Well, what do we have in common up here? We have an e to the 2t and e to the 2t. So we can probably pull that out. What do we have left over? Well, we have a negative 1 here. And we need to be careful, right? Because there's a negative and there's a 2. So negative times 1 times 2, negative 2, negative times negative t, positive t times 2 plus 2t, all over e to the 4t. All right, so we'll write this last piece here because this simplifies, right? These will cancel out. So we have 2t minus 3 all over e to the 2t. Awesome. I'll put a box around that, and we're going to end up shifting that over here. All right, so this is our numerator. So we'll write it here. Yeah, this is fine. Right, so our numerator here, let's write out the full, well, let's just write out the full thing. So we have d squared y dx squared. We have our numerator, which is that, 2t minus 3, all over e to the 2t, divided by dx dt, right, which is just another e to the t. So, upon simplifying, right, this e to the t just flips into the denominator. We have 2t minus 3 e to the 3t. Right, so that is our, let's get that, there we go. That is our second derivative. Now there's still the last question that we want to ask about concavity. Right, so I mentioned we want to set our second derivative equal to 0. Why? Because we want to find inflection points. Now notice here, right, this thing up here, the numerator, if we set that equal to 0, the entire thing will be equal to 0. We also know about the denominator here, that this will never equal 0, right? 0 is not in the range of e to the 3t. It'll actually always be a positive value. Okay? So, with that being said, all we need to do is set our numerator equal to 0. And that's not too tough to solve for, right? We get t is equal to 3 over 2. We draw our nice number line. We put 3 over 2 dead center, or wherever you want to put it. And we need to test on each side, right? We're plugging our test points. I'm going to do t is equal to 0 over here, and t is equal to 2, into our second derivative, right? That's going to tell us our concavity. So if I plug in 0 over here, I end up with negative 3, which is a negative number, divided by a positive number. This will always be positive, so this is going to be negative. Okay? And over here, t is equal to 2. 2 times 2, 4 minus 3. Positive 1 divided by a positive number. We will get positive. Again, 3 over 2 is neither of those. It's an inflection point. So we know, let's do a different color. We are concave, let's do down first, right, where this negative sign is, so negative infinity to 3 over 2, and we are concave up from 3 over 2 to positive infinity. Awesome. Okay, so again, introduced our new rule, parametric equations, dy dx. We have an easy e to the t. We end up with a product rule and a chain rule, baby chain rule hanging up out there. Right? We did some nice algebra to simplify. After we have our dy dx, which is hanging out here, we had to take the derivative again with respect to t. Right? So we end up with a quotient rule. Again, we simplify. That gives us our numerator. Our denominator is already done for us. After we simplify again algebraically, if we're interested in the concavity, right, we just draw our number line and we have some test points. So in this case, right, we have two sections, concave up and concave down. Okay, that is it for example 2. In our next questions coming up, we'll go through area. So think about what we've done already. We introduced parametric equations. We did first derivatives, which we've also seen here. And now we've done second derivatives and concavity. So now we will talk about some integral calculus with parametric equations. All right, I will see you in the next example. So far, right, we've done intro to parametric. We've talked about first derivatives, second derivatives, tangent lines that go with first derivative, concavity. Now finally we will introduce integral calculus, right? So we'll just write up here, integral. And I'll just put parametric. Right now, we're only going to go through one type of problem here. And so the idea is, if we are trying to find the area of, let's say, somewhere between A and B, which we'll specify later, right, we're going to have, well, let's actually write one more piece down. So let's put a comma over here, just so we don't forget our notation. We've been using f of t for x, and we've been using y as g of t. Right, you can flip-flop the order, but just to keep everything the same, this is what we've been using to notate. And so let's say my first one here, and I'll specify why it's in this order, we're going to say g of t times f prime, so the derivative of f of t, dt. dt. Geez, dt. Let's see if I can fix that quickly. That's fine. dt. Okay, now the question might be, well, why is f prime, right? Why does f get the derivative? Well, the reason is, if it says enclosed by the x-axis. So the relationship we want to make here is if we are enclosed by the x-axis, we are taking the derivative of whatever x is here, right? And we can say the same thing the other way around. So we have a is equal to from a to b, right? Integral from a to b. And now we're just going to flip the order, right? So f of t times g prime of t dt. And this is going to be, right, if we're taking the derivative of g, which is associated with y, we're going to be enclosed by the y-axis. And this part is specified, right? This and this will be specified. So again, y-axis, g is related to y. This is the one we're taking the derivative of, right? So as far as the integration goes, right, this is again something we're bringing back from our previous course. So we're just adding this new piece. Essentially, we need to make sure we have the bounds correct, a and b, and we need to make sure we're taking the right derivative of whatever function, meaning whatever axis we're enclosed by. So I'll give us an example here. Best way to learn. So let's do, I'm going to tell you that we're going to be enclosed by the y-axis. So we'll specify that we are enclosed by the y-axis. And now we need to define, right, our x and our y. So we'll say, we used a lot of blue here, let's go with we'll say x is equal to t squared minus 2t. And we'll say that y is equal to 2 square root of t. Okay. So, first thing we need to look at is we're enclosed by the y-axis. So, we want to take, right, the derivative of our g of t, which is 2 square root of t. And to make this a little bit easier, I'm going to rewrite it as 2t to the 1/2. And maybe we do some side work immediately, right? So what is the derivative? We'll just write, we'll write it here as g prime of t is equal to, well, the 1/2 comes down, right? So 1/2 times 2, and I can even write that 1/2 times 2, t to the negative 1/2, which is just t to the negative 1/2. Yeah, that's fine. I switched the problem a little bit, but it shouldn't affect anything. Okay. So we have our g prime of t. We already have our f of t. It's done. Right? So let's go ahead and write out what we have so far. We have our integral. I don't know my bounds yet. That's a thing, right? I don't know what my a and b are. We have t squared minus 2t times t to the negative 1/2. Okay? And of course, don't forget, what are we integrating with respect to? dt. Now, if I said we're enclosed by our y-axis, think about that. Let's draw that over here. I'm enclosed by this y-axis here. Right? What is my x value when I'm enclosed by this axis? Well, my x value here is equal to 0, right? X is equal to 0. If I'm enclosed by my y, my x value is equal to 0. So if you're wondering, how do we find these bounds? Well, we just need to set our x equal to 0. And that will give us our 2 t's, hopefully. Right? So set x equal to 0. We have t squared minus 2t. Maybe we take out a t. We have t minus 2. And now we have 2 different values, right? 0 and 2. So now we have everything. And hopefully this becomes not too bad of an integration problem. Let's see what we have. So let's simplify. Running out of space. We're going to end up with t. This is 4 over 2 times negative 1/2, 3 over 2, minus 2t to the 1/2 dt. And we just have some reverse power rules, right? So now we're adding and then dividing, right? So we end up with we'll end up with 2/5 t to the 5 over 2, right? So we added 1 to 3 over 2 to get the 5 over 2. We divide by 5 over 2, which is the same as multiplying by the reciprocal. That's how we get that 2/5. So minus 2 times, we're going to add 1 here, so we'll have 3 over 2. We'll divide by 3 over 2, which is the same as multiplying by 2/3. We'll squeeze that in there. And we need to evaluate from 2 to 0. Okay, so let's simplify all of this first. The 0 is going to be nice, right? So we really just need to worry about the 2. I'm running out of space. 2/5, 5 over 2, minus 4/3, t to the 3 over 2. And again, from 2 to 0. Okay, so this is our last step. I can write it over here. If I plug in 2, what is 2 to the 5 over 2? All right, so now we're going to have, we don't have to worry about the 0. 0 will be 0. So we have 2/5. This will now be, well, this is going to be what? 4 root 2? So if you're wondering how I did that, right, this is 2 to the 5 over 2. This is equal to 2 squared 1/2. I don't know if this is, yeah, this is fine. So 4, something happened, 4 root 2. I don't know if that's the correct notation, but it does evaluate correctly. 4 root 2 minus, and we do the same thing here. So we have 4/3, right? And then we end up with we're going to have 2 raised to the 3 over 2, which is another 2 root 2. Sorry, guys, I know I'm going into the deep corner here. And essentially all we're doing is simplifying, right? We can't get rid of the root 2. It's going to stay in place, right? We're not going to simplify that. But after some algebra, so way deep in the corner, we should end up with 16 root 2 all over 15. So sorry about writing all the way to the corner. In case we're wondering how did we make this jump, right? We could have factored out a root 2, right? This 2 gets multiplied here. We have an 8/3. We have an 8/5. We found a common denominator, right? And we should be good. I'll do some side work just so we can see it. But we have 8/5. There's one more part that we need to add here. Yes, because maybe some of you have done this. So really quick, maybe some of you are wondering, how is this positive, right? Ooh, where do I have some board space? Really quick. So if we would have graphed this, what you would see is this shape here is hanging into quadrant 2, which is a negative space. So the reason why this becomes positive is you have this negative sign hanging on the outside. I will clarify this in the next video. Right, and then this was also a negative. So the 2 negatives ended up canceling out. I will go over this in the next video. Hopefully we got everything else. The negative sign, a quick explanation since I've run out of board space in the next example. But just so we go through it. So the key wording here was enclosed by the y-axis, right? Enclosed by the y-axis. That means our y function, which is g of t, we took its derivative, right? We got t to the negative 1/2. That's how this ends up here. The f of t stayed by itself. We did some algebra to simplify, right? And then we just evaluated. Now again, the key thing here is, why did this become positive? Well, area is going to be positive, but this is in the second quadrant, right? So that's how we ended up with this negative sign. If we evaluate this algebraically, we end up with another negative sign, and they will cancel out. Okay, so I will go over that one more time in the next video. Until then, I will see you shortly. Okay, so we have one more example to do. Same idea. Now, I'm going to start us off by saying this one is enclosed. Let's get this marker to work. Enclosed by the x-axis. Right, so that tells us immediately which one we want to use for the integral. Let's write it on the side just so we know. A is going to be equal to the integral from a to b. G of t does not get changed, right? Because we're enclosed by the x-axis, this will be f prime of t dt. And in case we forgot, we're typically using x is equal to f of t, and y is equal to g of t for our notation. Okay, so we're enclosed by the x-axis, and now we need some equations to deal with. So let's say x is equal to sine of t, and we'll do y is equal to sine of t cosine of t. We'll see if we can get that marker to work a little bit better. Okay. So since it is enclosed by the x-axis, again, we're taking the derivative of sine. So let's write out what we have. I'm also going to give you, in this case, the bounds. We'll say from 0 to pi over 2. So sometimes you'll have to solve for them. Other times they will be given. So we'll leave y as is. That's g of t. We'll take the derivative of sine, which is cosine of t. And we want to simplify this. So we'll simplify it over here. Pi over 2, 0. I'm going to write it in this order. Cosine squared of t sine of t dt. Okay, so now we're looking at this integral. We need to recall all of our skills from integral calculus on which method to use here. So we have cosine squared sine of t. Hopefully it looks somewhat familiar. we were going to say over here, and again, this is the part that you might need to review, but we're using u sub. So I'm going to say u is equal to cosine of t. That means our du will be negative sine of t dt. Now, in order to make everything nice, I'm just going to move this negative sign to the other side, right? So we'll say negative du is going to be equal to sine of t dt. And now we're just going to interchange everything. We'll get to the bounds in a second. So we have the integral. This now becomes a u squared. We'll put the negative sign on the outside. U squared du. That's an easy integral for us to solve. And we also need to make sure if we're setting u, right, to be cosine of t, let's switch out the bounds. So cosine of pi over 2, 0, and cosine of 0 is 1. Awesome. And our last step, reverse power rule. This is going to be u cubed over 3, and don't forget that negative sign, evaluated from 0, or from 1 to 0. All right, so this will be a negative value here, in which we'll have negative 0 minus 1/3, or in other words, we just end up with 1/3. Right, so a little bit less work than the last one. Right, 0 to pi over 2, notice that this is in the first quadrant, so we didn't have to deal with any sign changes. So in this case, right, I told you it was enclosed by the x-axis. That means we need to take the derivative of sine. This is how we get this cosine here. This is our g of t, it stays the same. We combine the two cosines. We have a u sub problem. Make sure you get your du, right? Nice case, this will cancel out. Don't forget about the negative sign. And don't forget about replacing the bounds, right? If I switch over to u land, I need to switch out the bounds as well, right? After solving, we get 1/3, and not too bad. So if you did struggle, as I always mention, think about where we struggled, right? I would think the main thing here is this u sub, right? Maybe getting to this step wasn't too bad, but as soon as we went to go integrate, we forgot all of our methods from last semester, right? So we do need to refresh on those. We have a nice u sub, and after we've done that, the integral ends up being pretty nicely with just, right, a reverse power rule. Okay, that is it for this example and the video. I will see you guys in class.